Okay, so today we're going to be doing chi-square tests for independence. We're going to do it in relationship to our projects that we're going to do over the next 2 weeks that you'll be designing on Friday. But in order to design it, you need to know something about the statistical process involved to analyse it. As you know, you should have measured out some space. We went out, we explored Hyde Park, we've measured out some space, and within that space, you guys are going to have to figure out a way of randomly dividing up that space so you can have random numbers in order to collect data. The data that you're going to collect is whether or not a species is present or not, using quadrats. And I would expect in the space that you're using that we can possibly get up to 100 quadrats down and see whether or not species A is present or species B is present, depending on what species you're doing, you name each species. In order to do that, we're going to do something called chi-square test for independence. It's used in biology, standard level and high level, and it's used in mathematical studies as well. And it may be used as well in an SL project, for example. So it's something that you could use. It is a process that you could use. I'm going to do it by 2 different ways today. I'm going to show you how to calculate it effectively by hand, but obviously using the calculator to help us with some of the basic numeracy of it. And then I'm also going to show you how to use a matrix on the calculator and skip all of these steps so you can calculate it on the calculator. Why? Because in a project you'd want to be able to show the steps, but it's nice to use the calculator to do it quickly, and in an examination you can use a calculator and do it quickly. So that's an important thing to know. So if you're actually writing a report, you would write out step by step by step each bit that you're doing. So, just taking a look then, we're going to look at 2 different species. Today we're going to look at species A and species B. Whenever you set up a chi-square test, you have to set up a hypothesis. Okay, and we set it up as a null hypothesis. So we have a null hypothesis, and we can have an alternate hypothesis. When you do math studies, you'll also put the alternate hypothesis on there. But here today we're just going to go for the null hypothesis to start off. And we're going to say it's the chi-square test for independence, and independence is the important word here. Okay, so we're going to say species A, oops, because I already messed it up. Species A is independent of species B. So looking in our urban ecosystem that we're going to use, we're going to say that one of our species is independent to the other species. It doesn't rely upon the other species. And that's our null hypothesis. The alternate would be species A is dependent on species B. So that's the alternate hypothesis. Now we're going to test this. We're going to see whether or not it's right. In biology, which is again slightly different from our studies, we're going to test it to 0.05 significance, okay, so 5% significance. That's what we're going to look at, and I'll explain that a little bit more after. But in terms of what we're going to do now, we're going to take a look, we're going to pretend we've gone out, we've thrown all those quadrats down, and we've observed something. We've got an observed frequency. So you've gone out, you've laid them all down, and you put a quadrat down, and there's both species present. If there's both species present, that's going to be a number to this box here. Species A present, species B present. You put another quadrat down, at random. Species A is absent in this quadrat, but species B is present. So that would be a number there. Okay? I'm going to pretend we've put down altogether 60 quadrats. And in 17 of those quadrats, both were present. Does that make sense? In 21 of those quadrats, species B was present, but species A was absent. In 15 of those quadrats, species A was present, but species B was absent. And the remainder, they were both absent, and that's 7, and that should total 60. Okay, we work out our totals for each column, and I'll talk about that in a minute. I'm just going to write this here. Okay, green equals expected. Not expected, sorry, equals observed. So that's our observed, what we saw, what we tested. Okay? So we can total those up now, and we can total them up in the end, and we should get 38, and then we're going to get 22, and we're going to get 32, and we're going to get 28. Is that correct? Anybody see anything wrong with that? No. So our overall total is 60. So that's as if we did with 60 quadrats. You might do 100, you might do 50, I don't know. We'll work it out. It depends on our time and the time spent in the park. And our green is our observed values. So the next step is to calculate something called expected. This is what we observed, but what should be expected from these numbers? So looking at probability, we're going to look at what's expected. I'm going to skip a couple of steps and just go straight into calculating an expected value. You can ask your maths teacher for the mathematics of it. I'm not going to do that. So, in terms of blue, now I'm going to put our expected values. And all you need to know is how to calculate those expected values. You may be asked to calculate those expected values, and we're going to calculate those expected values by taking the totals. So if I'm looking for both present, I'm going to take the total at the end of present and the total at the end of present here. So those two totals, does that make sense? So present across and present across, so both present. And I'm going to take those two totals, I'm going to multiply them together. So I'm going to find the expected for, I'll put a little p here and a little p here, present, okay? So in order to calculate that, I'm going to take the total values, 38 times 32, and I'm going to divide that by 60, okay? Does that make sense? There is another way of doing it, okay? I could take the probability of this, which is 38 over 60, the probability of this, which is 32 over 60, multiply them together, just take the two probabilities, multiply them together, and then multiply it by 60, and I'll get the same number. So that's something I could do. But I'm going to do it this way, and you should do it this way, it's quicker. Okay? And that calculates out at 20.3. I'm not going to put that into the calculator there, I've already done those calculations. Okay? So the expected is in blue, I'm going to put them in brackets, is 20.3. Does that make sense? Good. Okay, so 20.3. And I can do the same here. I can do 22 times 32 divided by 60, gives me the expected for present species A, absent species B. So I can do exactly the same. Or I can work out the rest of the columns just by looking down the columns, which is another way. So 20.3, what do I need to get to 32? Well, I need 11.7. Does that make sense? So 20.3 plus 11.2 equals 32. So I can look that way. Or I can subtract 20.3 from 32 and it'll give me the expected value. I can calculate them that way rather than calculating more expected values by probability. So across this way, we've got 20.3. I've got to get to 38 and I'm going to put 17.7. And the last one there, 11.7. I've got to get to 22 and I'm going to have 10.3. So they are all my expected values. That's what I expected to have. Okay. However, the green ones are the observed values. I'm going to compare those now. I'm going to compare them to see whether or not this is a test where species A is independent of species B. So, what I'm going to do to do that is I'm going to move over to this calculation. And I've actually taken up a little bit of my board, so I'm going to just get the board wiper. Or not. Oh, there we go, over there, thank you. I'm just going to remove these, you should all remember that now. And we're going to use this calculation. I'll separate the board a little bit. And we're going to use this calculation. So this is the chi-squared calculation for independence. There are other chi-square tests. There's a chi-square test for goodness of fit, for example. That's when it's not a two-way table. This is a two-way table. Okay. So in this test, we use this calculation. So we're looking for the sum of observed frequencies minus the expected frequencies squared, all over the expected frequency. So we have to do that. The sum of means we do it for each square in our column. Yeah, it could be a case that you actually have more squares in your column because there's more options. We're just doing a presence-absence piece here. So it might be that it's longer than what we're doing, but we're doing the sum of 4 different numbers, effectively. So we need to start to calculate that, and we're going to write those across. So you could actually go through it with me, but what are we going to have? We're going to have this. We're going to say, yeah, I'll carry on in blue. No, I won't. I'll change the red. Keep the colours different. We're going to have equals here. We're going to have observed frequency, which is what? And this one's 17. Sorry, can't help but talk to you. And we're going to have minus the expected frequency, which is 20.3. We're going to take that, we're going to square it, and we're going to divide that by the expected, which is 20.3. Okay? We're going to do that for each square, so we'll just work across. We've got plus 21 minus 17.7 all squared over 17.7 plus 15 minus 11.7 all squared over 11.7 plus 7 minus 10.3 all squared over 10.3. Okay, and that's each block calculated. And we can put that into our calculator. We can use a series of brackets in order to do this all at once. Or if you're not so sure, and I'm just going to show you steps, you can do each part by part. But the problem with that, when you do it each part by part, is you start to round. When you start to round, you might make errors. Okay, so you're starting to look at what number you're rounding to. Are you using significant figures? Are you using decimal places, for example? For this example here, I'm going to use 2 decimal places. I'm going to stick to 2 decimal places as I move through, and I get 0.54. Just my calculation here. And then for the next one, I got 0.62. And for the next one, I got 0.93. And for the next one, I got 1.06. And this is going to give us a chi-squared value. We add them all together, it gives us 3.15. Okay, so that's what we've ended up with at the end of that. So we've ended up with the number 3.15. Now that number doesn't mean much to us at all. We need to actually take a moment and we need to take a look at degrees of freedom in order to work this out. And we need to take a look at a critical value as well. So those are 2 items we need to use now. So we need to take a look at degrees of freedom. So I'm going to take a look at degrees of freedom. And for degrees of freedom, we take the number of rows minus 1 and the number of columns minus 1, and we calculate that. And these degrees of freedom help us with what table to go to, what table we're going to look at. So in terms of what we're doing here, we take those degrees of freedom. We have 2 rows and 2 rows. Okay, nice and easy. So 2 minus 1 is 1. 2 minus 1 is 1. We get a degrees of freedom of 1. So that's what we're left with. Now when we get degrees of freedom of 1, if you're in maths studies, you go, oh no, because you're not allowed to have a degrees of freedom of 1. You would never be given a question with degrees of freedom of 1. You have to use something called Yates's correction in order to work that out. But actually here today we don't. We can just carry on. It's fine in biology, so we just carry on with this degrees of freedom as 1. I'm just going to pop this screen down for one moment, and I'm going to pop these critical values up, and you might not be able to see them very well. They're a screenshot, okay, taken from the Hodder textbook. And what we've got here is degrees of freedom for a 0.05 level of significance. Okay, so degrees of freedom, 1, 2, 3, 4. These are what you need to memorise. You only need it. Can I zoom in on trackpad? Ah, there we go. Perfect, thank you. So, all you need, okay, in this situation, okay, is for 0.05. In maths, you might use 0.01 or you might use 0.1. For you guys, 0.05 for biology. And these are always the same. I can show you how to work these out on a calculator if you don't remember them. They're quite easy to work it out on a calculator. But we're going to use 3.84, and that's what's called our critical value. So our critical value, okay, using our table of critical values for degrees of freedom, critical value is 3.84. Now what that means, okay, is our chi-squared value is less than 3.84, and because it's less, we have to accept our null hypothesis. So in this situation, we've accepted our null hypothesis because this value, our calculated chi-squared value, is less than our critical value of 3.84. If it was greater than 3.84, okay, we reject our null hypothesis and we can state that species A was dependent on species B, but at this point, we can't do that. Does that make sense, guys? Excellent. You can pause it a second.